end user product using KVM in what we call an HPC cloud. An HPC cloud, and HPC in general, we know it's just a very, very overloaded word. So first off, a couple of things that what we think is an HPC cloud. First off, we say the cloud should accommodate any real network configuration. We don't want any limits on there that we say it should have 3 CPUs or a big storage server or a small storage server. It should. Well, that helps. Okay, so any real network configuration should be supported, from private IP addressing, public IP addressing. It should include options to give oneself DHCPs, all that sort of stuff. So a lot of flexibility. And of course, it should be at least as fast as a common physical network. And why do we want to have a cloud? Not because we want to make things slower and less flexible. It should be faster and even more flexible. And that's one big part of being in a cloud is it should be highly available. I can move my servers about, they're virtualized, so they shouldn't crash, there shouldn't be any outage. I expect as a client that they don't overheat either, because I don't want to have a virtual air conditioner or something that one might dream up with. I just want these things to work, not overheat, not get broke. That's the highly availability feature on there. And of course, the real services, we have some additional features in networking, like firewalls and load balancers, which I say something about. They also should be available in this environment. And apart from all that, it should behave just like a real data center. If I rent bit in a cloud, it should be like a real data center. So that's sort of our vision. How my boss approached me a year ago and said, this is what I want you to build. I said, okay, let's try that. So we looked at a few things and came up with KVM, because KVM has got a unique flexibility in that area and a nice openness to it, where we decided this is something where we can build on. In the presentation here, I will say sort of the patches that we did, the problems that we came up with, and a few solutions in the future where we're going with our patches as well. Quite clearly, the cornerstones of this HPC cloud is the storage. It needs to be fast and reliable, and consistent is a must. Can't have inconsistent storage. We need a network layer that's fast, which is multi-tenant. That's very important, as you've got users on there that are either don't know each other or shouldn't know each other, either different departments or different companies. CPUs, they need to support the above. Yeah, there's a very close indication between the network layers and the storage, how well they behave, depending very much on the performance of the CPUs. And I discussed network and storage and how we found they relate to CPU cycles and what we can do to make that a little bit more tuned. We start with storage. Some things we tried, and quite clearly we can say this wasn't so nice. We tried NetApp, we tried Cluster, and we tried ZFS, and we all found problems with it. And this is something I was pleased to hear from Marcelo earlier on, because the consistency on snapshot, that was our problem with all of those. You have to freeze the VM in order to take a snapshot, and clearly in an HPC cloud, this is less than desirable. So I'm very pleased for everybody who hasn't seen that. It was a nice thing that we now get that with raw and QCOW files as well. We did find some ways to do that with current Linux tools. So saving yourself a bit of a headache, what we did is basically we used the monitor to flush the caches. We stopped the VM briefly, exactly then when the journals are written, which we know by the write barriers, and we mirror with DM, with the device mapper over to ZFS storages, and that way we get a consistent file system, because we have had just the point after the write barrier. We do stop the VM for a brief second, but that is only to initiate the snapshot. That's the storage consistency, where we of course have the problem, of course the guest OS is limited to the access to the guest OS is limited to the virtual machine owner, not the cloud administrators. So again, we can't install a backup agent on the virtual machines. That is something that we need to handle on the layer in the cloud, which makes this trick about the consistency far more difficult, because we need to get the timing just right, that the stuff that the guest thinks has been written are really written and part of the snapshot. Yes. And of course, these backups have to be taken online, because the client just expects that there are backups. If one of our data centers should ever go up in flames, then the client ideally shouldn't notice any of that. And if the client notices, then hopefully just for a second or two without losing any data. And that's why you can't take the machines down regularly and say, let's do a backup. But we did find that some snapshotting solutions, including the ones, say, some, like LVM or so, we have problems that the snapshotting gets slower and slower. And if you do that every few hours, then after about a week, the drives are no longer usable, really, because the speed dropped to something that just can't be used anymore. But synchronizing the snapshot to the write barrier turned out to be a fairly safe way, where we found that particular operating systems, which are very nice and colorful, they do seem to like being synchronized to a write barrier, because that's when they fire up nice and clean afterwards again. We found that we can do a lot of optimization in the elevator. We found that when we did our measurements with where does the data travel, we found that the elevators actually compete with each other. We found that the elevators in the guest and on the host and on the storage system had a different idea how they should order these write requests. That not only did that break our DMA, the elevators decided to buffer cache in between. And at the end, we found the only thing that actually does know how to run the elevators and how to do the block ordering was the storage systems themselves. They're the only ones really who know in which order it's best to write, because they're the only ones who know how the head is positioned at this particular point in time. Although the other elevators, of course, they just increase latency, and they have, apart from that, they really have little benefit, just the opposite. So we found it's a little difficult to disable that on the virtual I/O and the guest. It's easy to do on the host, but on the guest, if you don't have access to the guest, that's a bit difficult. And for that, we need a common indicator. So we thought of, we've tried a few methods like attempting to say it's an SSD device, the VirtIO block, rather than a hard disk. But really, in order to get that into all the operating systems in a consistent way, there is a lot of work needed where we need to speak with the operating system vendors as well, because not only Linux in the world, there appear to be still others around as well, which we do want to virtualize as well. A side effect of elevating, as we found, it's a nice effect. It increases the I/O block sizes. So we're trying to get as much data out of the guest with one interrupt, so we can decrease the context switches. They tend to be expensive. We indicate larger block sizes to the guest. In our device, we can actually say our block device has an 8K or a 16K block size, at which point the guests transfer more memory in each request, again eliminating interrupts, because that is where the CPU comes in, which just keeps killing our performance, and we max out the CPUs with all the context switches that we have to do at that point. So we're trying to limit those down to as little as we can. Again, then what we also need is, of course, replication. What do we do there? We have a few things at hand with KVM, but really what we found works best for us is if we mirror on the block device level. In our case, we just have a couple of block devices. They are mirrored with each other. It gives us the benefit that during a live migration, we can actually claim that this is a single drive as well. So if we do a live migration from one storage system to the other, normally you have the problem that KVM gets a bit into trouble there because it wants to access the same device. However, I want to show that here in a little graphic. If you mirror very simply the array 1 on which the virtual machine lives, then whilst that is replicating to array 2 and is consistent at all times, then the virtual machine can, of course, live migrate between the two storage scenarios. Yeah? That way you can also then have a flexibility in optimizing usage of the storage array so that you always have a reasonable utilization of your storage arrays and equally distributed. Far more fun was the networking part. That's a very interesting topic. We did try a few approaches on hardware, and comes to mind SRIOV and VTAG, all the cloudy type of things. But as soon as we go into SRIOV, then of course, at the moment at least, we use the live migration because we can't take the state of the network card as is and migrate that to another network card because either the network card is incompatible, it's a different one, or we simply don't have access to the firmware state on the card. So we lose our live migration, which for high availability criteria is absolutely crucial. Furthermore, if we go the route and do hardware virtualization and hardware filtering, hardware exposure of the network card to the guest, then we lose the option to filter the traffic. And this is important for us because we do want to offer real service like the data center, say firewalls. So we do want the net filter aspect of it as well. So we do need some sort of software layer around. We can't bypass the stack altogether. But just hardware at the moment isn't an option. We have also then used VLAN and VLAN, IP tunneling, tried a few things and found they're not particularly performing. Part of that, and equally with the network software that we currently use, the Open vSwitch and the Linux bridging, the problem that we found here is that we're always breaking out into Usernet at some point. And these switches, if you want to go into speeds of 10 gigabit and beyond, they're costly. They're really, really costly. And we found that with the current Linux and KVM tools, we're getting around 1.5 gigabit, 2 gigabit if we don't use the hardware offloading, which for reasons spoken in the slide earlier, we can't use at this point. And this, of course, was a problem. But there's a solution to that. And we have actually done the vhost modifications, where the first one, the obvious one, is we do a 64K MTU to the guest. Again, this reduces the interrupts. And further, we added routing information to the SKBUF as we received it from within the vhost, completely bypassing QEMU, completely bypassing the kernel host stack, the TCP/IP stack. All we did there was we take the SKBUF out and add our routing information, our routing tag to it, and put it straight onto an outbound interface. This was the single most important change that we found where we increased the performance. Funny enough, another thing that we found, and this is useful little message on the hardware vendors, we found disabling the CRC of the network card improves performance. Particularly on Intel CPUs, we actually have a CRC that works much, much, much better than the ones for the network cards. It's just faster. And of course, all the routing information we're trying to keep very disjunct from the actual routing layer. So we have very, very few lookups. We found it for clearly in these sort of speeds, every memory access, every walking of a B tree in RAM cost really performance. So we have a very, very slim set of routing information, a table, a flat table that we create from a different application, our management application, pre-configure our virtual network cards, and let them route as fast as they can and let them do that in fast speeds. Also, multi-threading the vhost helps a lot. You find a few patches that are already for the multi-threading now in KVM. This has given us from the 1.5 to 2 gig, we came up to 7 gigabit per second. Now, if I say 7 gigabit a second, we all have seen slides that said 10, 15, but we're taking 7 gigabit. This is from a wget on one virtual machine on one server, on one host, to a virtual machine on a different server, once straight through a single wget TCP stream from wget to Apache. And that gives us a sustained 7 gigabit. And that's really what we want to see the performance with, when we say, this is what the client actually gets. This is a real live test. I can say from iPerf and from NetPerf what we also tried, but this is our key figure that we say this is something where we want to improve and increase the speed. And this is mostly done, most of the speed really is, what we learned is if we go bypass the host kernel as much as we can. In our case, we have a little bit of overhead still for the net filter, which we do want to hook in. But apart from that, we move straight routing through. You can see it's
by network or by I/O? I'm assuming you're reading from disk over the network right to another disk?
Neither. It is neither that. We have a network that can handle, needless to say, let's say more than 10 gigabit. That's not the limiting factor, and this was straight from RAM. The file was cached by Apache in RAM, and in wget we wrote it to dev null. And it was literally, it was the speed of the CPU that was blocking us. As I mentioned, multi-threading, we have got a multi-threading vhost patches there, gives us, of course, better throughput. When you have the first approach that we did, we said, well, let's see how fast we can use lots and lots of cores to assemble our TCP stream, which basically made all the other virtual machines stop if one was very busy running TCP streams. So a bit of adaptive pinning was necessary, where we said the user processes of KVM are the same, pinned to the same cores as the processes on the host for vhost. So effectively, the VM regulates itself. The faster it can use its own CPUs to assemble the stream, the faster the host will send them out. There comes then the fun, of course. If you do have a single VM that has, say, 4 virtual cores and trying to send one that is 1 core, you will not gain much, very clearly. But it just needs to match. The sender and receiver, both at this point, are very, very fragile. They both need to have the CPU performance, or they will just not perform. You can't expect, say, a 1-core CPU to receive or send traffic in speeds of 7 or 8 or even more gigabit a second. It's just not something that we found. You will need a minimum amount of cores for that to be handled. And here comes the next fun, but if you have a cloud like that, and you know that your networking speed is limited by the virtual machine, we suddenly thought, now what do we do if we want to do firewalls on a multi-tenant environment? You can't put boxes in between, physical box, as you would in a real data center. You can't even put a virtual machine in between, because that would become the limiting speed of the network. If you have 7 gigabit, if you know you can do 7 gigabit on a single TCP stream, if you firewall 2 machines, you would get 3.5 for each. That's not going to be good enough. So we figured we need to distribute those as well. Here we modified vhost in order to have direct access to the NetFilter tables. This is partly a patch to NetFilter, because NetFilter's API, non-API really, didn't really allow for that, and part patch to vhost. Essentially, you rethink of something where you have a firewall that would normally filter VM 1, 2, and 3, which you would have on a host or perhaps on a machine in front of that. We modified our management system to recalculate rules, and secondly, also to produce that in each vhost, we have access to the IP table, so that we get into a scenario more like that, where the same firewall rules are held 3 times on the different servers, so that each virtual machine can be handled by individual cores. Again, these are the same cores that actually are for the KVM host processes, so again, they start utilizing them in a distributed manner. Basically, the more virtual machines you will have, the more cores you will have, the faster your globally distributed firewall will work. This also helps us to manage the speed that the client can expect. From that, we get a very, very little overhead from NetFilter. Our initial tests have showed that we're under 10% of network speed if we do it that way. So we can keep scaling upwards. Our upstream commitment, I said we have a few patches ready here. Of course, our measurements show that the standard KVM, we go up from 1.2 gig to 7 gig. This is something that, together with, I don't exactly remember the names, some people on the KVM mailing lists we have worked with, and we would like to introduce a vhost direct routing API. Funny enough, during my time here that I've been enjoying to hear speeches here, I have noticed that there is a lot of effort to bypass QEMU and bypass some of the higher layers. This is pretty much what the vhost direct routing API would offer, that you have memory areas out of vhost which you can directly take and send out to other things. Mac VTAP would be a particular application, or even Open vSwitch. You would essentially quite speed up the process if you don't have to go through the host TCP IP stack. That's something that we will be introducing in order to speed the development of new high-speed networking devices up. On parts of high availability, we can present a bit of improvements as well, particularly in CPU was interesting. If you wanted higher availability, then of course if you want to scale up and down, you need to be able to do that without shutting down the machine and starting down the machine. So this is a very, very important feature for KVM. And the CPU hot plugging, we managed to get the patches into the latest C BIOS, and on KVM some they're still flagged as very experimental, but do feel free to use them if you're brave, and in a developer state they do tend to work for us quite well. RAM we're working on is far more complicated, but should also be something that we can expect to get into KVM soon, hopefully. From the CPU hot plug, we have also very carefully looked at the KVM native tool, because it does just appear to be a very lean way of hot plugging. And we had a big question mark, where do we go with Chemo? It makes it very, when Anthony has this morning said few things that he's going to clean up the code in Chemo, which we thought this is probably a very good idea, because we found it very difficult to add anything to Chemo really at this point without investing lots of money just to get him to know it. So we're looking out for the KVM native tool and put a few bit of effort in there as well.
So what's your use case for CPU and memory hot plug?
The use case?
For the hot plug or hot plug or hot and plug too?
Both. The use case is very simple, really. If I have a network that I utilize more during the day and less during the evening, then I would like to unplug my CPUs, because I pay less during the evening then.
So you want
it's quite simply.
Hot unplug too?
Hot unplug and
does not work today, and it doesn't work with Windows at all.
We noticed that with Windows it still has Windows has a few issues doing that. With Linux we managed to get that to work.
Because I know Windows does not support
Quite so. Quite so. You're absolutely right. We do need a driver for that. As far as we got it with Windows 7, Windows 7 says this device cannot be hot plugged, which is the CPU 0. If we do it with CPU 1 and force it to unplug, then funny enough it simply stops, because the thread that said do you want to unplug then stops, which is not particularly helpful, but that's quite some work that needs to be still completed, yeah. That's a Windows driver issue.
So you need Windows driver to
for that you would
plug CPU?
Or modifications of some sort. In plain Windows 7 we found the unplugging does not work. You're absolutely right.
And hot unplug with Linux does not work currently in KVM?
The CPU hot plug in Linux now works.
Unplug?
Yes.
It's not with Res and kernel.
Now we have made some patches there as well that we have published about a week ago. As I mentioned, do use them if you like. They are quite experimental, but they seem to work.
Where you publish them?
In the KVM mailing list. No? There was some work that was necessary, indeed, yeah. Mm-hmm. Okay, question answered. Then CPUs, where do we want to go with hot plug and unplug? Just to pick up on that, because what we found is that the network hardware some network hardware is fairly good nowadays in the latency, and it becomes quite feasible to start scheduling work across high-speed links. One of the examples where we tried such things experimentally was using InfiniBand. You can there use the same or similar method as the live migration, where you start moving some page across the wire and have the cores on different physical machines work simultaneously on the same virtual machines. In theory, so far, we have gotten that you have a single virtual machine that spans multiple servers, which of course gives you lovely scalability. But this is the vision that we are implementing, and I would be very happy for anyone who would like to work on such a project to contact me after the fair, because it's something where we're very visionary and interested to move on with that. Okay, thank you very much. Are there any questions?